Okay, well, we definitely have a popular answer. Now, how do we do this? Let's remember that this vector equation really tells us a lot about the components of these two vectors. It tells us the x component of the force vector is equal to the charge times the x component of the e vector. The y component is equal to the charge times the y component, and the z times the z. Well, the charge is not zero, and that certainly tells us that the x and z components of the electric field must be 0, right? So we've only got a y component. The force on a proton was in the negative y direction. So what does that say about the direction of the electric field? Negative. Okay, so it better have a negative y component. It better have 0 x and z components. And there's actually only two possible answers. This one, you forgot to take into effect the fact that there's this q here, right? So you have to divide by q. And so I believe that 4 is the right answer. We have negative 4.8 times 10 to the minus 16 divided by positive 1.9 times 10 to the minus 19th, and we get a negative 3 times 10 to the third newtons per coulomb. Okay? All right. We did not get to the electric field due to a point particle, and I think that it might actually be a good idea to do this, and we do have a moment, so let's do this, because you're going to need to do some exercises with this. We, in fact, do have a vector equation for the electric field at some location created by a point charge. And it looks a little scary. It looks like this. E at some location, so there's this implicit r here, is equal to a constant, which is written as 1 over 4 pi Greek letter epsilon sub 0. It's sort of a funny way to write a constant, but there's a reason for that. Q of the particle divided by, there's the magnitude of the relative displacement vector squared, r hat. What does that mean? It says that if we've got a particle here, say a proton, and we draw a vector r to an observation location here, then the electric field due to this particle points in the direction of r hat, which is this little unit vector here. There's a constant which has the value 9 times 10 to the 9th Newton meter squared per coulomb squared. This is just the magnitude of this vector. So this is the 1 over distance squared dependence you were talking about at the beginning of class. It depends on the charge of the particle. If the particle is positive, it goes this way. If it's negative, it goes the other way. And so if this is a proton and our observation location is here, what does that tell us about the direction of the electric field due to the proton at this observation location? You just point. Okay, here's the vector part, the r hat. Here's a positive number. So it points in the direction of r hat. So the electric field is going to be like that. And notice that we're now drawing things with two completely different dimensions on the same picture. This is units of meters, and this has units of newtons per coulomb. So of course, it isn't really going to be the same size. We have to do some scaling to make this come out right. Okay, this isn't really all that hard to do. You can do this because you just calculated the magnitude of a vector. You know how to do that. You know how to find a unit vector. You know how to multiply by constants. And so, in fact, that's the way to calculate the electric field. Very quickly, we'll do one real quick numerical example here. If this r vector is let's say it's 3, -4, 0 meters. Say we have an object that's some kind of macroscopic object, a little charged ping pong ball or something with 3 times, let's make it a proton. Let's make it 1.6 times 10 to the minus 19 coulombs. Then the magnitude of r square root of 3 squared plus 4 squared, that's clearly 5 meters, right? R hat, I will tell you, is it's 3, -4, 0 divided by 5, and that actually comes out to 0.6, -0.8, 0. And so to get this whole thing, we take E is 9 times 10 to the 9th Newton meters squared per coulomb squared, 1.6 times 10 to the minus 19 coulombs. We divide by 5 meters, the quantity squared. We multiply by 0.6, -0.8, 0. And it comes out to be some number in newtons per coulomb. And what I actually get is 3.5 times 10 to the minus 11, -4.6 times 10 to the minus 11, 0 newtons per coulomb. So it is kind of big, but you just chug through it. There's nothing magical about it. Okay? You'll probably have to do that for homework.